Differential equations, type 2, real-world power resistance. So in 1994, we have a car of mass 1,000 kilograms moving with a velocity v along a horizontal road. And it's moving against a constant resistance of 1,500 newtons. And we're given that the engine is working at a constant rate of 75 kilowatts. So the first thing we have to do is show that the acceleration is given by 150 minus 3v over 2v meters per second squared. Okay, so if we're looking at our car moving along a road, so we draw a lovely little car, and we're knowing that it's moving along the road, then what we have to look at are all of the forces that are acting on it. Okay, so we have an engine driving the car. So basically this is our driving force, or what's known as our tractive force. So the force coming from the engine pushing along the road. But we also then have the horizontal road causing resistance, slowing the car down or trying to stop the movement or the motion of the car. So the first thing we have to do is try and find our acceleration. So we have to look at how are we going to do that. So because we're given power here, we're told that the power that the engine is working at a rate of 75 kilowatts. Now power is normally given in watts, so we're going to rewrite that as 75,000 watts. And we know the mass is 1,000 kilograms, and we also know that the resistance is 1,500 newtons. So if we're looking at power itself, well, we know from our maths tables that power is work over time. But what we don't really use that often is the fact that power is also equal to the force times the velocity. And this can be found on page 55 in your maths tables. So it's one that students often forget because we don't use it that often. And we really don't use it that often at all in physics. We're generally always using power as work over time or voltage by current if we're looking at electrical power. So here we're looking at the force times the velocity. So if I rearrange that to get my force, well, my force in this case is the tractive force of the engine. So the tractive force can be written as the power, which is 75,000 watts, divided by the velocity. So now we know what T is. If I look at my net forces, we know that F equals ma. Well, it's accelerating forward, so I've drawn in my diagram here to the right. So my leading force will be my tractive force of the engine, and my opposing force is my resistance. So therefore, if I sub that in, what do I end up with? Well, I end up with 75,000 over V minus the resistance, which is 1,500 newtons, is equal to the mass, which is 1,000, times the acceleration. So if I go on to the next page, then I can actually get my acceleration on its own. So I'm going to get my lowest common denominator there to be V. So that gives me 75,000 over V minus 1,500 V over V. So in other words, I can add those two together, and that will equal 1,000 A. So I want to get A on its own now. So if I divide everything across there by 1,000, then I can simplify that down by dividing the top and the bottom by 500. So in other words, I end up with 150 minus 3v over 2v. And of course, obviously, I should put in there my units as meters per second squared. And that's the first part done. Okay, So for the second part, it says calculate, and we have to be careful here because it says correct 2 decimal places the time taken for the car to increase its speed from 0 to 25 meters per second. So if we look at what we know, well, we've just established that the acceleration is given by 150 minus 3v over 2v. So if I look at my start limits and my end limits, I can then decipher, am I going to be using dv dt or v dv ds? So at the start, we know that the initial velocity is 0, and we also know the time is 0. And at the end, if we go back, we can see that the end speed is 25 meters per second. So the time taken to do that, so the change in time is what we're looking for. So if we're given v and t, we're going to write our acceleration as the rate of change of velocity with respect to time, so dv dt. And therefore we're going to get all our v's on the left and everything else on the right. Now, unfortunately, we have a v on the top and the bottom here. So when I rearrange that, I'm actually going to get 2v over 150 minus 3v dv is equal to dt. And if I put in my limits, my upper limits are my end limits and my lower limits are my start limits. And we can see that on the left-hand side we have a bit of an issue because it's not a constant over a linear function, in other words, a log function. So what we're going to have to do is we're going to take that to the side and we're going to do a little bit of long division. So I'm going to rewrite that as the variable first, so minus 3v plus 150, and we're dividing that into 2v. So if I divide minus 3v into 2v, I end up with minus 2/3, and if I multiply that back out, that gives me 2v, and minus 2/3 times 150 then is minus 100. So if I subtract, so in other words change the signs, that becomes plus. I'm left with 100, in other words this is my remainder. So it's not going to divide in equally, okay? So in other words, 150 minus 3v is dividing into 2v minus 2/3 times plus 100 as a remainder where it won't divide in. And now that looks a bit more user-friendly because I have a constant over a linear function, which will of course be our log functions when we integrate. Okay, so if I integrate minus 2/3 with respect to v, that gives me minus 2/3 v. And if I integrate the 100, so again, if you don't spot that that's a log function, take out the 100 as being common, and you're left with 150 minus 3v, and you should be able to see a little bit clearer that that is your log function. So it's the natural log of the denominator, but I have to also divide by the derivative of the denominator, and the derivative of 150 minus 3v is of course minus 3. So I'm dividing by the derivative of 150 minus 3v, and that's within the limits of 25 and 0. And if I integrate the right hand side, well, that's t, and my limits are t and 0. Okay, so let's sub in my limits. So I'm going to have minus 2/3 times v minus 100 over 3, if I just tidy that up, times the natural log of 150 minus 3 times 25. And then, subtracting your lower limits. So minus 2/3 times 0 minus 100 over 3 times natural log of 150 minus 0. And that's equal to t. Sorry, a bit of a squeeze there. Okay, so let's tidy this up. So therefore that means if I just bring the t to the, I'll just switch sides there, we have t is equal to, well, minus 2/3 times 25 is minus 50 over 3, minus 100 over 3. So natural log of 150 minus 75 there is natural log of 75. And then 2/3 times 0 is 0, so that is minus 100 over 3. Natural log of 150. Okay, so again we have a bit of our log rules here. So again we're looking at a log minus a log. So this is page 21 in our maths tables for our log rules. So if we have log x minus log y, well then that's log x over y. So here's our log x and here's our log y. So we're subtracting them. So if I go on to the next page, well, what does that give me? It gives me t, sorry, t is equal to 100 over 3. So minus 50 over 3 plus 100 over 3 natural log of 150 over 75. And of course you can put all of that into your calculator in one go as well, which then just gives you 6.44 seconds. Okay.